All right, so did everybody come up with 5? Anybody come up with more than 5? Okay. If you did come up with more than 5, that's probably because you found ones that are actually the same as one of the ones that's up here. It just maybe looked a little bit different. Okay, the first one is the straight chain one. Okay, what do we call this? Hexane. And typically to indicate that it's in a straight chain, we call it normal hexane or N-hexane. All right, what about the second one here? Across to the right. What's the longest chain? 1, 2, 3, 4, and 5. Okay, so it's a pentane, and it has a methyl group as a substituent, so this is methylpentane. Notice that's one word. Okay. Is that done?
No, it needs to be 2.
All right. It's 2-methylpentane. Okay, the next one has the longest chain of being 1, 2, 3, 4, and 5. So it's still a pentane. It has a methyl group on there, so we call that a methylpentane. Okay, and it's on the 3 carbon, so it's 3-methylpentane. Okay, now what I want to kind of point out here is, what about 4-methylpentane?
You start counting the other way.
Right. If I were to put the CH3 at this carbon here, think about what I will have done. I would have changed the order in which I should be counting, right? I should be counting from right to left then, because the first substitution would happen closer to the other side of the chain. Okay, so what we have here is 3-methylpentane. 4-methylpentane, it will be the same thing as 2-methylpentane. Can we have a 1-methylpentane? What would that be? It'd be N-hexane, correct. All right, how about the next one on our list here? We have the longest chain being 1, 2, 3, 4 carbons. So it's a butane. Okay, and I have methyl groups on the 2 and 3 carbons. I need to indicate that there are 2 methyl groups. Okay, so instead of just saying methylbutane, I'm going to say dimethylbutane. But I need... No? Oh, I thought you were telling me I was wrong. It's okay. I've been wrong many times. So it's dimethylbutane, but I need to be able to indicate where those methyl groups are. And where are they? 2 and 3. So the way that that is shown is by going 2, 3 dash dimethylbutane. Now I know that people start getting really uncomfortable when it comes to these dashes and these commas and this weird punctuation that's taking place in the name of this compound. Here's the easy way, or maybe not the easy way to remember, but here's the rundown on how to remember. You always put a dash between a number and a word. Okay? Anytime a number and a word are adjacent to one another, there should be a dash. Anytime 2 numbers are adjacent to one another, there needs to be a comma. All right? Yes?
Could the methyl groups have been coming off of the same, like, second branch instead of having second and third?
Yes. Absolutely.
And then what would it be called then?
It would be the next compound over.
Oh, okay, all right.
Do you have a question? All right, so Brittany, right?
Yeah.
Okay. What Brittany was asking here is, what if this CH3 group right here were taken and moved to this carbon, what you get would be this compound. All right, where we have the longest chain being 1, 2, 3, and 4, so it's still a butane. Okay, I still have 2 methyl groups, so it's still a dimethyl butane. Again, notice all one word. But now I have to indicate where they are. Is it enough for me to say 2-dimethyl butane? The answer is no. It has to be 2, 2. And what do I always need between a number and a word?
Dash.
A dash. Okay, it's a 2,2-dimethyl butane. Yes?
Why can't you have an ethyl group there?
Why can't I have an ethyl group there? Explain to me. Oh, are you saying why don't I name...
Yeah, instead of having 2,2-dimethyl butane, why can't you have a 2-ethyl butane?
A 2-ethyl... Oh, because ethyl implies CH3CH2.
Right.
Okay, so are you saying that the ethyl counts here or as these two guys up here?
2 together, like
Yeah.
CH2 and CH3, you still have the C14, the C614, H14.
It's true, but the problem that you run into is that this is a methyl group. And this is a methyl group. And here's an ethyl group.
Right.
Which is the same thing as C2H5, whereas these guys added together would be C2H6.
Right.
So you can't use that same terminology there. And it also doesn't give you the structural information that you need. Unless I'm misunderstanding your question.
I don't know, I'll have to think about it.
All right, you let me know if I did. I'll be happy to revisit it. All right, so let's try some other stuff here. How would you name this?
Very carefully.
Okay, again, you can speak amongst yourselves and discuss this. Okay, don't allow yourselves to be hindered by your natural tendency to read from left to right. Remember the rules. Follow them blindly. All right, I'll give you another minute on this.
Yeah, but there's no they don't know second branch, like coming off the one. No, yeah, this is what's coming off the two.
It's the longest chain.
I would forget it could be one.
So start counting off that.
And then you no, because they're all coming off. I know there's two. Like it says.
All right. So the way this question was written, it has the classic pitfall for undergraduate organic chemistry, and that is, how do you count the longest chain? Most people have a tough time with this just because we're so used to looking left to right. So a lot of people are tempted to say, here's our longest chain and here's our substituent above it. That's not the case here, right? The longest chain so you got 1, 2, 3, 4, 5, 6, 7, 8, 9. So what is that? Let's see. Based on nonane. Now, the next question, where do we start counting from? Okay, the way you find that out is by counting from both sides and see which one's shorter. Unless you can just visually look at it. I can't. So I go, well, I could do 1, 2, 3, 4. So that gives the CH3 the lowest possible number, and that's kind of a rule of thumb. You want to give everything the lowest number you can give it. If I were to count from the other side, I don't know why I decided to go with a Christmas-themed color system here, but 5. It would be on the 6th. So, as you said, Carmen, we need to make sure we count from the bottom. So we have a functional group here. That functional group, we have a group attached here. What kind of group is that? Methyl. Okay. And if that's a methyl group, it's on the 4 carbon. What do we call this? Good. Okay, let's throw a monkey wrench into the works. Oops. It wouldn't feel like class if you didn't.
Nope, it would not. You would have to think you were sick.
Unless the stars. Sorry.
All right, so what do you think this is called? Well, first off, we need to look at the functional groups. It turns out that alkyl halides, the chlorides, bromides, iodides, don't really count as a functional group. So this is still considered an alkane. So what is the name going to be based on? The longest chain, which is how many, Greg? 3. Okay, so the name's based on propane. Okay, I have a substituent, a group attached here. What's that called? Well, chlorine, chloride, it starts getting kind of confusing. You might think based upon the alkyl groups that this would be a chloryl group, but it's not. Okay, for all the halogens, a chlorine is a chloro group. Bromine is a bromo group. And fluorine is a fluoro. And iodine is an iodo group. And astatine is an element that you will never see. So we're not going to worry about it. Okay, so in this case we would have 2 chloropropane. Not so bad, right? Okay, now it will be. Okay, here we go. Okay, this is when the party was starting to close down at the pub when they were talking about how to name compounds. Okay. There we go. That's a fun one. Okay, notice we now have two distinctly different substituents attached to the parent. Okay, the parent chain is how many carbons? 1, 2, 3, 4. So that makes this a butane. Good. All right. I have substituents. I have a methyl group and a bromo group. Where do I count from? From the right side, because that's where the first substituent is. It's on that one carbon there. Okay, so I know I have a 1-bromo, and I know I have a 3-methyl. Now, what were the rules I told you about punctuation in the naming? Two things you got to remember. What always goes between a word and a number? A dash. What goes between a number and a number? A comma. Okay. So this shouldn't be too bad. Okay. This is going to be 1-bromo dash 3-methyl, which I'm going to rewrite that for you. How do you feel about that one? Okay. All right. Okay. Now let's have some more fun with this. You see, by looking at this structure here, you might be under the false assumption that the reason why we put bromo before methyl was because bromine had the lower number, right? It's 1-bromo, 3-methyl. That kind of makes sense. The problem is it's not numerical order, it's alphabetical order that matters. Okay, so let's try this out here. Try and think of an example real quick in my head where that would be the case. Let's see here. Okay, there we go. Sorry, there's an error there. Let me erase this. Okay, how would you name this guy right here? Okay, where do we always start no matter what we're looking at? We're always going to look for the longest carbon chain. We've already kind of done the functional group check, right? Okay, there's nothing on there special except for halogens. So we have 1, 2, 3, 4 carbons again, so that makes this a butane system. Okay, again, I have 2 substituents, 2 groups attached to the chain. Where do I count from? Right to left or left to right? Wherever the first substituent occurs, which is on this carbon right here. So that's going to be 1, followed by 2, 3, and 4. So I have a 1-fluoro, and I have a 3-bromo. Because alphabetical order is what rules the order of the substituents that we name, this becomes 3-bromo dash 1-fluoro. See what I'm talking about with these kind of weird and crazy rules? Okay, it looks bizarre, but the thing is, it's consistent. And if everybody follows the same weird rules, we'll all arrive at the same structure given a name. Make sense? No, thank you. All right. Now, anybody here who had been exposed to organic chemistry through their general chemistry class probably had the impression that organic chemistry was all naming compounds, right? If you liked that, I'm sorry. That's not what we're going to focus on here. There's computer software out there that you can draw the structure and they'll tell you the name. You can tell it the name and it'll draw you a structure. The real interesting part of organic chemistry is how it allows you to kind of predict how things are going to work around you. You can understand the properties of the chemicals that you're using. I know you don't think you're using chemicals, but right now, Kari is opening up a bottle of soda. That's right, I'm from Philadelphia. It's soda, it's not pop or Coke, okay? And right now, she has opened up this bottle that contains phosphoric acid, caffeine, water, sugar, carbonic acid, which is now turning into carbon dioxide as we speak, and it's all encased in a shell of polyethylene, okay, which also contains some plasticizers. Now, everything that's going on in the world around you is chemical-based, whether you like it or not. The medicines you take, the foods you eat, the floors you walk on, everything is chemical in nature. Anybody here ever spilled something on themselves? I can't be the only one. I've got a 2-year-old, I've got a 6-year-old. All things have been spilled everywhere in my house. I am the master of stain removal. You know why? Because organic chemistry allows me to predict solubilities. I know what's going to remove a stain because I know the chemical properties of the stain and I know the chemical properties of the material that the stain has landed upon. And I can decide on which chemical to use to coax that stain out. As a matter of fact, a friend of mine, he works for Stanley Steamer, and he went and attended this big convention up in Chicago, and they were talking about how to handle really difficult stains in carpets, and he said, Doug, it was a chemistry lesson. The entire thing was a chemistry lesson. Okay, so organic chemistry, it can be really fun, it can be really useful. I want you to embrace it. Please don't think that this is just the mundane naming of things. You do need to know how to name things. But this is the fun part, the properties. All right, so let's talk about the properties. We're going to talk about the properties of every type of functional group as we proceed through the course here. But the 2 types of properties that we're most interested in are going to be the boiling point / melting point, which are intrinsically related to one another, and the solubility. Okay, you're going to be able to predict relative boiling points of chemicals just by looking at their structure or looking at their name. The same goes for solubility. Okay, the melting point and boiling point of a chemical is often misunderstood from a physical standpoint. Okay, we talked about bonds last class, right? What were the 3 different types of bonds? What do we have? Ionic, covalent, and polar covalent. Okay, so we have these different types of bonds. Sometimes people have the misconception that the process of boiling is a matter of taking those bonds and breaking them. But that's not the case. That's decomposition. That's reaction. Okay? Pure melting and boiling is this. The conversion of a solid to a liquid is going to be melting, And a conversion of a liquid to a gas is boiling. I know I'm telling you things that you already know. Okay? But I want you to think about what's happening as you go from a solid to a liquid. Okay, if you have a solid, okay, typically we're talking about a system where the molecules of a given chemical are packed pretty darn close to one another. Okay, they're packed so close to one another that they're actually interacting with one another in an intimate way that actually holds them together. Okay, when we go to the liquid form, typically speaking, this isn't true in all cases. Okay, those molecules are not quite so close together. They're not quite so intimately involved with each other's business. I mean, they're around, they kind of roll off of each other, but they're not locked next to each other. Okay, in other words, in a piece of ice, one molecule of water is locked against another molecule of water. Okay, and it will stay that way. But if you start to take that ice and warm it up so it becomes liquid water, those water molecules, they still see each other, they still interact with one another, but they're fluid, they move around. Okay, they can exchange with one another. Why? Because we've added energy. When you raise the temperature of something, you add energy to it. And when you add energy, you give it more freedom to move. Okay, and when we take a liquid and we heat it up even further, we are increasing the distances even further. Spacing it out even more. Ideally, we're spacing them out so much that each individual molecule does not interact with another one. Remember that ideal case, the ideal gas law, PV equals nRT and all that stuff? You don't have to do that here. I'm just asking you to remember it, so you don't have to play like you've never heard of it before. All right, so they space out even more. So I take a solid, I apply energy to it by raising its temperature, it turns into a liquid. I take a liquid, I raise its energy by applying, or I raise its temperature, thereby applying more energy to it to raise it to become a gas. Okay? Each stage results in the molecules being spaced out more and more. Now, here's where organic chemistry comes into this. What types of things are going to make two molecules want to stick together? We've already talked about one particular interaction. What was that? Well, electronegativity, the positives and negatives attracting one another, right? Opposites attract. Okay, so if you think about sodium chloride. Okay, you got your sodium bound to chlorine. Again, I don't know why I'm going with the Christmas theme this time. But then you get another sodium and another chlorine. Remember what this is called? It's the crystal, wrong color. Crystal lattice, right? Okay, I'm not going to go around trying to draw a perfect crystal lattice for sodium chloride. Now, has anybody here ever seen molten sodium chloride? It's about 800 degrees Celsius to get there. Okay, so sodium chloride does not want to melt. Why not? Well, it's starting off locked in place, right? It's next to its partner. It has a strong affinity for its partner. It's having an ionic interaction. It's not a bond, but rather we're going to call this an intermolecular force. Actually, let me move that. Okay, and there are several types of intermolecular forces, ionic being the strongest, followed by hydrogen bonding, followed by dipole-dipole, followed by dispersion or van der Waals. Okay, we'll call them dispersion, I don't care. London dispersion forces. And here's the fun part, folks. Dispersion forces, dipole-dipole, hydrogen bonding, ionic bonding, all of these are a matter of pluses and minuses being attracted to one another, just to varying degrees. In the case of an ionic interaction, we have a full-on positive charge bouncing up against a full-on negative charge. When we get down to dispersion forces, we're talking about a teensy tiny positive charge interacting with a teensy tiny negative charge. Okay? Of the two, ionic interactions or dispersion interactions, which one is going to hold two molecules together more strongly? Ionic, right? So, which one's going to require more energy to break up those intermolecular forces? Ionic. And if it needs more energy, which one is going to be which one's going to melt at a higher temperature? Ionic. Okay, so you can look at the forces that are holding together the molecules and predict whether or not the boiling point or melting point is going to be high or low. So let's get back into the realm of our alkanes. We have methane, okay? The prototypical alkane. What types of forces do you think are at play in holding one methane molecule against another methane molecule? Well, let's be careful here. First off, it's not ionic, right? No ionics. Or there's no ions. What about hydrogen bonding? In order for hydrogen bonding, what do you need? No. What's that? Right, the hydrogen needs to be bound to either nitrogen, oxygen, sulfur, there's another one, and the halogens too, I think. Yeah. Okay, but the big ones are nitrogen, oxygen, for our purposes. Do we have any of those elements present here? No. So can it be hydrogen bonding holding them together? No. Dipole-dipole. A dipole-dipole interaction would imply that we have a polar covalent bond. And folks, this is where the periodic table kind of misleads us. Where is hydrogen at on the periodic table? All the way on the top left-hand side. And where does carbon wind up? Kind of towards the right. You'd expect that they would have vastly different electronegativities. They don't. Carbon, I believe, is 2.4 and hydrogen's 2.2. Okay, hydrogen plays tricks on us. Okay, the hydrogen-carbon bond is non-polar. Okay, very non-polar. So do you think that dipole-dipole interactions are what's playing a role here? No. What's left? Dispersion. Dispersion forces are the most common forces that hold together our alkanes. Okay, because they're the only ones there. And are these forces strong or weak? Weak, okay? Terribly weak. How much energy do you think it takes to separate two molecules of methane? Not very much at all, okay? So would we expect methane to have a high boiling point or a low boiling point? A very low boiling point. Why? Because to get it to go from a liquid to a gas doesn't take much work at all. Doesn't take much energy at all. Okay, does that make sense? Now, with that being said, let's compare methane, which we've all experienced as as natural gas in our homes, maybe through heating or through cooking, and compare it to another alkane. One that I think that we have all experienced recently at the gas pumps. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Yes, octane. Now, frankly, there's not that much octane in your gasoline. Your gasoline's mostly hexane and heptanes. But octane, which is going to have a higher boiling point, methane or octane? Okay, we kind of look at it, but you got to remember, sometimes our brain plays tricks on us because we're looking at it like, octane's bigger, it's heavier, it's going to not evaporate off or something like that. I don't want you to think about it that way. I want you to think about the opportunities for dispersion forces. Dispersion forces, the way they work is that they rely on the ever so tiny difference in electronegativity between carbon and hydrogen to allow them to interact with one another and to be held together. For which one of these molecules, methane or octane, is the power of the van der Waals or dispersion forces greater? Octane. Why?
More hydrogen bonds.
Don't call it hydrogen bonds.
Well, more hydrogen bonded to the carbon. So
Right.
there's a chance to-
Okay. There are more opportunities for van der Waals or dispersion interactions the longer the alkane is. Does that make sense? Okay, longer